Here we go. So we're going to talk about sums and differences of the cosine. So let's look at the cosine. What happens here is maybe we want to find an angle like 75 degrees or something, and that's not really in our unit circle, or it's not on our chart or something like that. We can't find it, or maybe it's written in terms of radians, and it's kind of difficult to do. So let's start out with the example in the book here on page 205. And they have the cosine of A minus B. And so what they want to show you is a little example that the cosine of A minus B is not a distributive property. It's not cosine of A minus cosine of B. It would be too simple. Yes. We're used to everything being difficult, so that makes sense. So let's say we wanted to do the cosine of, let's say it said, what if A was pi over 2 or 90 degrees and B was 0 degrees or just 0 radians? Okay. So if we did it by distributing, we would think, okay, this is the cosine of pi over 2 minus 0. That's what it should be. And pi over 2, let's see if I can find pi over 2, the cosine of pi over 2, 90 degrees right here, the cosine is 0. So you should get 0 minus 0 is 0. The answer should be 0. If we distribute, however, we get the cosine of pi over 2 minus the cosine of 0, which is cosine of pi over 2. That's pretty easy to see. Cosine of pi over 2 is 0. Minus the cosine of 0. The cosine of 0 is 1. And we get a negative 1. You see, the answers aren't the same. If we just went ahead and subtracted these, we get 0. But if we distribute it out, we get negative 1 for our answer. So that's not correct. So what is the cosine of A minus B? And so you want to jot this down. The cosine of A minus B is the cosine of A times the cosine of B. Then we write the opposite sign here, plus, let me make sure, cosine, sine of A, sine of B. Cosine, sine, sine, cosine, sine, sine, cosine, sine, sine. It's kind of like a little musical number there, I'm sorry. But that's how it goes, cosine, sine, sine. Cosine of A, cosine of B, sine of A, sine of B, opposite sides right there. And what if we had, what if this was a plus sign? It's still going to be cosine, but opposite sign, minus, and then sine. And then notice these are in order, AB, cosine, sine, cosine, sine. So yeah, it's kind of weird. You would think that would be just cosine of A minus cosine of B, but it's not. So that makes it an interesting thing. And then they go ahead and prove it all, but we're not going to go through that. So on page 206, you can see, here's your goodies. You can see it, cosine, sine, cosine, sine. Because the sine, when we do the sine of A plus B, it's going to be a little different. So we kind of want to memorize this, so it's kind of interesting. So what we're going to try to do is try to find the cosine of 15 degrees. Okay? But you don't have the cosine of 15 degrees here. You got the cosine of 30, you got the cosine of 45, you got cosine of 60. So we try to figure out a way that we could write this as either an addition problem or a subtraction. Well, we couldn't do it as an addition very well, but we could do 45 minus 30, that would give you 15. Or you could do 60 minus 45, that would give you 15. So it really doesn't matter which one they used. In the book, they used 45 minus 30, so we might as well do the same thing. So they said, let's write this as the cosine of 45 degrees minus 30 degrees. Would that give me 15 degrees? Yeah, if I just subtracted them. But what is the cosine of 45 minus 30? Well, the cosine of 45 minus 30 is cosine, cosine, sine, sine. So it's the cosine of 45, cosine of, this would be A, this would be B, the cosine of 30, minus the sine of 45 times the sine of 30. Boy, I just made that on my paper. So cosine of 15 degrees is the cosine of 45 minus 30, which is cosine, cosine, sine, sine. Cosine of 45, cosine of 30. Sine of 45, sine of 30. So this
Would
is,
it be adding, Mr. Mitchell,
yes.
instead of subtracting between the cosine and
Oh,
sine?
yeah, we want to add them. Thank you. Thank you. Yes, opposite sides. Thank you very much. Yeah, because it would throw off our answer quite a bit. So then that's where you want to go to your chart here and try to find, these references. So cosine of 45 is radical 2 over 2. I just jotted over here. And what's the cosine of 30 is radical 3 over 2. Plus, now you want the sine of 45, which is radical 2 over 2. It's the same for both of them, huh? 45 is kind of a neat angle. And then the sine of 30 is 1 over 2. So you look those up in your table or using your unit circle. You can use your unit circle. Remember, this is cosine, this is sine, So however it's easier, I've got it also here. Lots of different ways. Okay, so then you multiply that out and see what you get. You get radical 6 over 2 plus radical 2 over 4, excuse me. 2 times 2 is 4. And you get radical 2 over 4. So we could leave it like that, or they probably put it together and they said, okay, this is radical 6 plus radical 4. So radical 6 plus radical 2 over 4. Cool, huh? So kind of a different thing, cosine, cosine, sine, sine. And it's in your book. Yeah, you get used to using them. Let's try another one. This one a little bit harder. We got, when they're in radical form, they're usually a little tougher. So we have the cosine of 5 pi over 12. So we could say this is the cosine of 3 pi over 12 plus 2 pi over 12, right? But you don't have that on your unit circle. Look at your unit circle. It's not there. So then we have to reduce it. This would be the cosine of pi over 4 plus pi over 6. Let's see if we have those. Pi over 4, pi over 6. See, so we got it. So now let's expand that out. Let me write it over here. Cosine pi over 4 plus pi over 6. It's not too hard. It's just a matter of putting it into the formula. I think it's easier to just write down the formula, cosine of A, cosine of B, minus, I'll get it right this time, sine of A, sine of B. Always the opposite. On the sine, it's just the reverse. When we're going to do the sines, they keep the same sign. So So far, so good. So this is going to be cosine of what? Pi over 4, cosine of pi over 6, minus sine of pi over 4, sine of pi over 6. Okay, and then we substitute in, here's your pi over 4, here's your cosine, the first one's, let's be radical 2 over 2, and pi over 6 is radical 3 over 2, and we're timesing these. Minus sine is the back one, radical 2 over 2, and 1/2. So this looks like radical 6 minus radical 2, and they're both over 4, so we just put it over 4, huh? And that's what the book came up with. So it's a little tedious, but not too bad. It'll get worse. Okay, and then we have, here's a third problem where they actually gave us the expanded form. So here they had the problem expanded out. This is in degrees. So we see it's a cosine, cosine, sine, sine. So when we put it back in, we notice this is going to be cosine of A plus B. So this is A and this is B. So this is simply the cosine of 87 plus 93. So that's simply the cosine of...
Can you scoot the paper up a little bit, Mr. Mitchell?
This would be the cosine of 180. So it's just 87 plus 93. It's just these two quantities. And what is the cosine of 180? Well, you can look on your chart. The cosine of 180 is -1. So this would be simply -1. So it's pretty straightforward. You just have to realize that cosine, cosine, sine, sine is the same thing as cosine of A plus the cosine of B. So you just kind of, it's just something you memorize, cosine, cosine, sine, sine. It'll probably stay with you the rest of your life. You'll be singing cosine, cosine, sine, sine. And that's pretty cool. Okay, another relationship is on page 207. These are the cofunction identities. Cofunction. So if you have the cosine, and these come in handy, of 90 degrees minus, say, theta, that's the same thing as the sine of theta. Okay, so let's say this was cosine of 90 degrees minus 45, then that would be the same as sine 45. Maybe this theta was 60. This would be cosine of 90 minus 60, which is a cosine of 30, would be the same as the sine of 60. The cosine of 30 and the sine of 60 should be the same. Let's take a look and see. Cosine 30, radical 3 over 2, sine of 60, cosine of 30, wait a minute, cosine of 60, 90 minus 30. Cosine of 60 is 1/2. The sine of 30 is 1/2. And this is weird because I have the cosine coming first and then the sine. I don't like that. But it's not a good reference one. That's what it means. Okay. And vice versa. Sine 90 minus theta. Whatever theta is, that would be the cosine of theta. So if this was a 60, then this would be a 60. Okay, we'll try some more. Tangent of 90 minus theta goes cotangent theta. Likewise, the cotangent of 90 minus theta is the tangent of theta. And finally, the secant and the sine cosecant go together. So secant of 90 minus theta, put it up a little higher, equals the secant, cosecant of theta, and the cosecant. These are in your book on page 207, or on the back cover, or on that sheet I gave you. So what it's really, well, let's try one here and see what it's really saying. It's really saying that if you have the cosine of 60 degrees, you could write that as 90 minus 30. So the cosine of 60 is 90 minus 30, right? Which is the same as the sine of 30 degrees. Here's theta. Here's theta. So the cosine of 60 and the sine of 30 are the same thing. If you notice, these two angles are going to add up to 90 degrees, right? So 60 degrees, 30 degrees, 90 degrees. So what if I had a cosine of 58 degrees? Then that would be the sine of 32 degrees. 58, 32, they add up to 90. You can just think of it that way, that these two numbers are going to add up to 90. Cosine of 58 and the sine of 32, they're going to be exactly the same thing. If you looked at the cosine of 58 on your calculator, or in fact, I got a calculator here. Clear it. We'll look up the cosine of 58. This calculator's not very good. 0.5299. Now let's look up the sine of 32. Sine 32. Wow, 0.5299. So that's all it's really saying. And that's a quick way of doing it, that these two numbers, the 48 and the 32, are going to add up to 90 always. Pretty cool, huh? So it kind of helps you a little bit when you're trying to find angles. Like if you know the cosine of one, then you can figure out the sine of the other. That's really all it's about. So let's try this one. And some of these you don't have to do a whole lot of work. Let's try example one here. This is on page 208. They have the cotangent of theta equals the tangent of 25. Well, 90 minus 25 is what? 65. So I can tell that these two numbers are going to add up to 90. This would have to be the cotangent of 65. You know, you can make it all fancy and stuff, but that's all really they're doing. They're saying this is the cotangent of 90 minus 25, which is 65. Okay. Sine of theta equals cosine negative 30. Well, this would be the sine of 90 minus a negative 30, because that's what theta is. I get fancy and write it out. And what's 90 minus a negative 30? Change, that'd be 120. So the cosine of negative 30 and the sine of 120 are the same. So theta is 120. I guess they wrote it that way. So theta is 65. The final answer, you know. Here's one a little bit harder. Cosecant of 3 pi over 4 equals the secant of x. So 90 is what? Pi over 2? Just write like that. Minus 3 pi over 4. Let's change this to fourths, huh? Multiply the top by 2 and the bottom by 2. So that would be the secant of negative pi over 4. So theta is negative pi over 4. Is that what they came up with? Yeah. Just a fancy way of writing 90 degrees. So these two numbers, see 3 pi over 4 and negative pi over 4, have to equal 90 degrees, pi over 2, will they? That's 3, take away 1 is 2, 2 pi over 4, reduce it, pi over 2 equals pi over 2. See, so these two things are just going to add up to 90 degrees. Same thing here. These two add up to 90. Where are we at? This and this add up to 90. So you're just using a 90 thing. Now, how about a tough one? This is where they get a little bit harder, is example 4 here. Let's see, what is example 3? It says write cosine 180 minus theta as a trigonometric function of theta alone. Okay, let's look at that one. They got the cosine of 180 degrees minus theta. And they want us to expand that out. Well, okay, this is cosine 180 cosine theta minus sine 180 sine theta. Change sign, plus, sorry. Okay, that good so far? What's the cosine of 180? The cosine of 180 is negative 1. Cosine theta. What's the sine of 180? The sine of 180 is 0. So you got 0 times the sine of theta, which is 0 times anything is 0. Okay. So the answer is negative cosine theta. And they wanted to write it in terms of theta. So just using this expansion, that's all it is. And then substituting in the values that you know. But now we're going to do one that's a much tougher one. Here we have a problem here where they said the sine of S is 3/5. And the cosine of T, different angle, is negative 12/13. They're both in quadrant 2. That's why this is negative and this is positive, quad 2. So they're both in quadrant 2. And we're going to try to find out what is the cosine of S plus T. Well, we know the cosine of S plus T is the cosine of S times the cosine of T, right? Minus opposite sign. The sine of S times the sine of T. The problem is we've got the sine of S, but we don't have the cosine of S. We got the cosine of T, but we don't have the sine of T. So how are we going to find those? Well, I like to do it this way. There's a couple of different ways. The book shows you 2 ways to do this, but I think drawing a triangle is the easiest for me. So I'm going to go down here a little bit and draw this triangle. Wait a second. We're in the second quadrant, so let's draw the triangle in the second quadrant. And let's start out with this one. Let's call this angle S, and the sine is 3/5. What does that mean? What is the sine? The sine is opposite over hypotenuse, right? So this side must be 3, and this is 5. And what we need to do is find this missing side. Then we can find what the cosine is. Well, we probably know that this is a 3, 4, 5 right triangle. But how do we get that? Well, we do that by using the Pythagorean theorem, that 5 squared equals 3 squared. Let's call this b plus b squared. Hypotenuse equals the one side plus the other side squares of those. So 25 equals 9 plus b squared. Take the 9 to the other side. 16 equals b squared. Take the square root. B is 4, but remember this is a plus or minus, and we can see if this is an axis here, this is a -4 going this way. 3 up and then 5. So what would the cosine now be? The cosine of S is the adjacent over the hypotenuse. See, those things we learned earlier come back, we have to still use them. So the cosine of this would be the adjacent, which is -4, over the hypotenuse, which is 5. So now we know the cosine of S. We could write it up here if we want to. Let's do it in a different color so we can see that. It wasn't originally there. Okay, now we got to do the other one. We have another drawing. It's in the second quadrant. And here we have the cosine. The cosine is the adjacent over the hypotenuse. So this is -12/13, excuse me. So now we want to figure out what this is right here. We know it's going to be positive because we're going up. So we just calculate. 13 squared, let's call this A, side A, equals -12 squared plus A squared. 169 equals 144. You can use your calculator, plus A squared. Subtract that off. 25. Of course, these are coming out nice. Yours won't. No, hopefully they will. Then you take the square root of that, plus or minus. We want the positive answer because we're going up, 5. So now we can figure out the sine of t. Call this angle t right there. The sine of t is the opposite over the hypotenuse, 5/13. And we can put that up here. So this is how I usually do it. I draw the diagram and calculate the missing one. If we knew the sine on this one, then it's easy to figure out the cosine. If we know the cosine here, we can figure out the sine. But draw it in the second quadrant when you make your drawing. That way you get your signs correct. Like if it's a -12 or a -4, you can get those numbers correct. Okay, now all we got to do is plug this back in. This would be the cosine of S, and we know the cosine of S is -4/5 times the cosine of t. Cosine of t is what? -12/13. So we go back to, that's why I wrote them up here, minus the sine of s, 3/5, times the sine of t. And sine of t was 5/13. Now notice these denominators are the same, which makes it kind of nice. So this is going to be positive 48/65 minus 15/65 equals 33/65. And that's our answer to this problem. But we had to do all this work to find these two missing items. So that's where the fun begins, huh? Now, you could also, if you want to, instead of doing it that way, you can use this formula, sine squared theta plus cosine squared theta equals 1. And say I have the sine of s, sine squared s plus cosine squared s equals 1. The sine of s was 3/5, so this would be 3/5 squared plus cosine squared s equals 1. Square that out, I mean, oops, sorry, you can't see it. I'm sorry about that. Square that, so I just put in the 3/5 because they had given that in the instructions. And I could just multiply that out, 9/25 plus cosine squared s minus 1 equals 1. Bring this over. See, what I don't like about this is now you're dealing with a bunch of fractions. Cosine squared s equals 16/25. And then you can simplify that to 4/5. But then you got to start, remember the cosine in the second quadrant is negative. So to me, I think it's easier to do it this way. That's how I prefer to do it. By making the drawing, I can visualize it better. I can see what's going on. Doing it this way, I don't visualize it as much. Plus, I'm dealing with a bunch of fractions, which might be a little harder to do. And then when I get through, I don't know if this is going to be positive or negative. I got to kind of think, well, what quadrant am I in? And is the cosine positive in that quadrant or negative? And this way, it's a little bit, I still have to kind of do that a little bit here, but I can visualize it better. I know that all students take calculus. So I know the sine is the only one positive in that quadrant, and the cosecant, of course. So you can do it this way. You can look at the second example in the book, but to my liking, I don't really care to do it this way as much because sometimes when you're using other things later on, we're going to learn these for the tangent and for other things, and it's a little bit tougher. You know, each one has its own special formula, so it's easier if you just stay with that. Maybe, I don't know. We're not going to do the voltage problem. So I hope this helps you get you started on these things. You can see that these problems are going to be the roughest ones to do. There is, one other thing, verifying an identity. We do want to do that. We do this real quick. They had the secant of 3π/2 minus x equals a negative cosecant of x. So you might think, okay, let's use a 90 minus theta thing, but I really don't think that's going to work very well in this problem. So we're going to actually write this as 1 over the cosine of 3π/2 minus x equals, we just keep this coming down. We're proving an identity. Then what I'm going to do is expand this out. Remember, you can't just distribute. It's not cosine of 3π/2 minus the cosine of x. It's cosine, cosine, sine, sine. So this is going to be the cosine of 3 pi over 2 times the cosine of x plus, this is 1 over that, the sine of 3 pi over 2 times the sine of x. Okay, well, let's look up the cosine of 3 pi over 2. Cosine of 3 pi over 2 is 0. So 0 times the cosine of x, that's just going to be 0. Plus, what's the sine of 3 pi over 2? The sine of 3 pi over 2 is negative 1. Okay, this might be a little harder to see. Negative 1, see. This is negative 1 times the sine of x. So that's negative 1 sine x, which is, now remember, this is 1 over this. I'm kind of goofing up here. So that's, let's bring this negative 1 to the top. That'd be negative 1 sine x over sine x like that. And if we bring this up to the top, remember that becomes the cosecant. So this is negative 1 times the cosecant of x. And there we go. So this is negative 1. Or you could write, maybe we could have kept it positive. I don't care. 1 over the negative sine of x is the negative cosecant of x. Yeah, so I get a little carried away here and forgot to put these over 1, under 1. So yeah, proving these things is not always the easiest. It's sometimes kind of tough, but you're going to use, obviously, you're going to use this expansion in there somewhere. That expansion is going to come out because they want you to learn that expansion. So all these problems, you're going to have something, you're going to translate to the cosine, you're going to have a parentheses and you're going to have to expand it out. Or it might be expanded and you might have to make it smaller, So you're going to use this theorem, these identities. That's the whole idea behind them.